Hi, everybody. Welcome to class today. I want you to start by thinking about these two questions, namely, what's the effect of having a coefficient in front of the x? What does that accomplish in a rectangular graph? And then think about what that might accomplish when it's a polar graph. So everyone think about that and chat about it for a few minutes. Okay, so someone in the chat area, what generally happens when you put a 2 in front of, when you have any coefficient bigger than 1 in front of the x, in a rectangular graph we're talking now? Decreases the period is correct. What else can we call that? And yes, if it's a 2, it halves the period. What else do we say about when there's a number in front of the x like that, as far as what transformation, geometrical transformation happens? Yes, stretch if it's a fraction. You'd actually call this a horizontal compression, Ivan. Horizontal compression because the range won't change. It will still stay between -3 and +3. So there's a horizontal compression, and that's why the pictures of these two things look like these, where from 0 to 360 we get two periods, two full periods instead of just one. Well, we're going to see what happens in graphs, in polar graphs now. So if it was 3 sine theta, if that 2 wasn't there, this thing would be a circle. And let me bring that circle up for you. Okay, so here I have Desmos. And if I make A 3, got a nice circle there. That's 3 sine theta. Now, what if I were to change that? I'm not going to do it yet, but let me bring back the iPad. Okay, so here is coming up the iPad again. There we go. This is not going to become a circle. And I'm going to make a couple of observations here. First observation is any point on the x-axis ends up becoming a point on the pole. So the fact that there are these 1, 2, 3, 4 x-intercepts, all 4 of those are going to end up being poles in the at the pole for that graph. Now, anytime you see something that resembles a parabola, so I'll make this nice and darker. Here's like a parabola looking thing. Well, a parabola thing always ends up looking like some kind of a petal of a flower on, so I have the red starts here and ends here. And halfway between, in this case, this is 180. This is 90. So halfway between, this high point is at 45. So I have a point here at 45, 3. Somewhere over there. And what happens is that it becomes kind of like a loop. Now, there's a lot of kinds of loops I could make. I could make like a loop that's kind of like a circle. I can make a skinny loop. There's many widths of loops that are possible. But the trick is, and this is very important, I'm about to say, because this loop, this parabola thing is between 0 and 90, if over here I make a line at 0 and a line at 90, like that, I want to fit my loop so that it sort of starts off tangent to this line. It kind of comes around and then comes back and kind of hugs the corner there. So it looks a little bit like the petal of a flower. But just because it's going to be happening soon, if this thing was a skinnier curve and it was like from 0 to 60 degrees for whatever reason, because there was and this was 30 in the middle, what that would cause is I have to fit my loop thing between 0 and 60 now, so it would be like a skinnier petal. And in the extreme case, where it was just y equals sine theta, that actually still was like a petal, but it was from 0 to 180. So my lines were like that, and the petal ended up becoming a circle, actually a perfect circle. But this stuff all kind of agrees with each other. Like the fact that when there was no coefficient in front of the x, it became a circle, was just a special case of this idea of the petal. I'm gonna, well, now this next, the next portion of the curve, which I'll make blue, this is a little confusing because it's negative. First of all, it's between 90 and 180. So I could make this 90 line and this 180 line, but the petal is actually not going to be in quadrant 1. Instead, let me extend it like this, and the petal, take a look at what happens. First of all, it's nice to get the maximum point. Here at 135 is going to be at -3. So 135 is pointing this way, but -3 is that way. And the petal is going to look like this. But what I want you to realize is that this point right here at like 100 degrees actually corresponds to this point over here. So if I were to like draw this in order, it would go first here and then loop like that if I actually watched it graph like in order. Now there are four parabola looking things. Here's the third one. And this one is above the axis. So it's like what we'd expect. It's from 180 to 270. So that one is going to go like that. Gets to its maximum. And then finally, this one here, notice that at, this is 180. This is 360. This is halfway. 180, 360. $270. So over here at 315 degrees, it actually is this point right here, because 315 is pointing that way, but it's negative, so it makes that one. And it is going to make this petal. But if you're wondering which portion did it make the petal in a counterclockwise fashion or a clockwise fashion, you can look at like a point like over here at like 275 degrees. So I'd be pointing in 275 would be pointing, a little bit in this direction, and it would make this point. So it would actually go around that way. Let me bring up a thing so we can watch this, watch it get drawn. And think I have a link to this for you. If not, I will add one in. Where is, I need Mr. Stir's thing. Where is it? Hold on a second. Here we go. And I will provide a link to this for you because it really is instructive to mess around with this. Let me see if I can have many windows that you don't see. Let me go like that, see if that's better. Actually, I don't know if you can see that. Okay, let me go back to the window. So this one was 3 sine 2 theta. So I'll click here. Oops. Three sine 2 theta. Oh, this is good. And animate P. Check it out. Loop 1. There's the second loop. There's the third loop. And there's the fourth loop. Incidentally, if I make B1 and I do the same thing, animate, there's only 2 loops. There's the first one, and there's the second one that's upside down. That's the one that makes the perfect circle. Also useful, if I make this a 2 and I say show angle lines, show petal order, a lot of stuff Mr. Stir made. So we can see the order that the petals happened. You could also see the red ones are for when the it was below the x-axis.
When when B is odd, does it just layer it over itself twice?
That's what we're going to find out. So when B is odd, there's going to be like when B was 1, there was only 1 petal, but there were 2, but they were superimposed on top of each other. But when B was 2, there were 4 petals. So let's take a look at what happens. That's actually what the next question is. So let me bring the iPad back. Actually, that's not the next question, but that one is coming. Here's a question for you to think about. This is y equals 3 sine 6 theta. So there's going to be a lot of these half parabola things. So there's a lot of petals. Why don't you take a minute to think about what do you think this picture is going to look like? How many petals do you expect to see? And what do they generally look like? And in what order would the petals be drawn in? So you take a few minutes. I'm going to pause the video as you think about that.
Let's see. I think you're on mute. We can't hear anything.
Thanks a lot. So as I was saying, I had to extend the guidelines, the 30 and the 60 guidelines, so that because this pedal had to be drawn in like quadrant 3, and by extending the guidelines, I could fit that second pedal in between there. So it's very far away from the first pedal. And the third pedal is between 60 and 90, but that one, because this is above the axis, is going to go uh, just the way we expected, like that. And when you do this all, and I'm going to switch now over to the Mr. Stir thing. Here it is. And this thing is really useful. So I will, this was, it's 3 sine 6. I want to, hold on. I don't want to see the curve. I'll reset. Okay, so when I change this, to change that to 6, make this a little bigger if I can. Okay, so watch, I'll even throw all this stuff in. Okay, check it out. Here it comes. The first pedal, the second pedal, the third, the fourth, the fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. If you look closely, you'll notice that the order of the pedals is, it goes, the odd number pedals go exactly where we would expect them to be. So the first, third, fifth, seventh, ninth, and 11th are all going in the way we'd expect them to be. But the even number pedals, they're going like this: 2, 4, 6, 8, 10, 12. So they're both going sort of clockwise. And it is, it is pretty confusing, but I recommend, and actually Mr. Stir, no, he does have this one, graphing polar equations. And in this one, you can type in any function you want. So in this case, well, I thought you could type in any function you want. If b is not a whole number, then your rose curve will not end at 360. It will sort of it will end short. And this is not letting me change that. That's too bad. Okay, so now let me get back to the iPad. Both of the examples we've seen so far have an even coefficient. This one had a 2. This one had a 6. And you notice how the answers both had symmetry. They both had pole symmetry, and they had all the different kinds of symmetry. Now, what happens if there is a +1 at the end? Well, this is going to get to be a pretty strange looking picture, the +1. The issue is we still are going to have like 4 parabola looking things. See, there's one like this. Now, this first parabola is kind of interesting. What's interesting about that first parabola that we haven't seen before? Someone could type that in. What is it about this red thing I just drew that's different than anything that's happened before? Yes, it's before it doesn't start at 0, 0. And then we have our second one is going to be smaller than the first. So we're going to have big petals and small petals because our petals start and end at the x-axis. And then I'm going to have another large petal and another small petal. Now, to draw a nice accurate graph of this, Notice how this first petal, we actually don't even know what the x-intercept is. And my eyes aren't very good. I can't even see what it is approximately. But we do know that if I go from here and make this line, here's one full cycle of the curve, and here's the second full cycle. So that would be 360 with the 2 cycles. So this would be 180 over there and 90 over here. So it's slightly bigger than 90. That's the main thing. And it also starts, this red one starts slightly before 0. So I'm going to go like this. I'm going to make my guideline just a little bit below the 0. And I'm going to make this, because it's not these 2 points that matter. It's the actual x-intercepts that matter. That's what forms the petal. That one's slightly bigger than 90. So I'll go like that. And my first petal, well, the high point is going to be at 4. The other ones always had the high points at 3. It's halfway between, approximately. It's hard to draw exactly where it is. Like, is it? Oh no, actually, it's not. It's actually at 45. The center is actually at 45 still, because it's the peak of the parabola of the sine curve, even like that. So 45, 4, somewhere over here. This is. And when I draw this, I start hug that guideline, and then come back to hug the guideline again. And that's our red petal. Now the green petal, it starts at this place, and it ends over here, which is slightly less than 180. But because it's negative, I actually have to extend these guidelines, and its low point is at what is it? Is it -2? It's -3 plus 1, so -2. So it's actually a small petal like that, and it's going to be graphed like that. So we have these like different sized petals. The blue one is going to go something like that. And the yellow one is going to go like that in that other place. See, the yellow one's in quadrant 4 here, but because it's negative, it ends up getting flipped into quadrant 2. So we get this kind of weird looking butterfly looking thing. And when I come over here to the Mr. Stir rose curves, we can see that if I put this in, oh, his doesn't give us the ability to put a +1 in there. Oh well. I think if I instead go here, we can't see it drawn in the order, but we can see if I have a 3 sine 2 theta +1. Here is, see what happens when I change. Oh, and maybe I should show you now. Here's 2, and here was 6. So 6 made 12 petals, 4 makes 8 petals, 2 makes 4 petals. And when I throw the +1 here, check it out. And if I make it different, the petals get smaller and other things start happening. Okay, what I haven't done though yet is what happens when the coefficient is odd. And here is a question for you to think about. Actually, I'm going to actually put you into groups for this. This should say r equals 3 sine 5 theta +1. And what's new about this is we've never had an odd number here. And I'm going to put you into groups to think about how would you describe the answer. If you want to take a second, when I put you into groups, I think you lose the, oh, good question. Someone asked about cosine. That's a great question. I'll put that up at the end. For now, I'll just do sines, but at the end, I'll throw up a cosine and see what that does. Great question. I'm gonna put you into groups though. If you want to make a little picture of this thing, just to see what's going on. You know, this is 3 sine 5 theta plus 1. It's got a lot of branches. Okay, I'm going to put you into the groups now. Let's see how I do that. Breakout rooms, get ready to be in 10 breakout rooms, and I'll put you in there for about 7 minutes. Ready? And here you go.
I believe so.
Wait,
In
which
this case,
with the odd number?
For the 5 theta, like would it just have
Oh,
like
yeah.
5 petals?
Is it double that number?
that's for even, I think.
I don't know if that just works
Oh,
for
yeah, I know what you're saying. Yeah, that's for even. Yeah, then for odd, it would be 5. Yeah.
yeah. That might work.
Yeah, but then does the +1 change some things though?
Yeah, it kind of like, well, it makes the petals like awkward shapes, but it also kind of like makes it more diagonal, I think.
Right, because like, remember like when he showed the circle, how it was technically like 2, but it looks like 1?
Yeah.
So I think it's the same thing for this one, but because of the +1,
Zoom recording. I'm not. Someone tell me, am I just in one room now, or can a lot of people hear me? I'm
You're in the main one.
main one. Great. So first of all, I want to show you something about what happens when I make something odd. So when this is with c equals 0 first. So when c is 0, we get these flower-looking things. But notice that when b was 1, there was not double the amount. It was just 1. But when b was 2, it was 4. Well, when it's an odd number and c is 0, the number of petals will equal the number of will equal b. And that's because of the overlap that happens. So if I come over here and I change this to someone asked about cosine, this will be a good way to show that afterwards. Here is one. Okay, I'm not able, here we go, let me swing this up. So this is sine, cosine 3 theta. And the reason why there's only 3 petals instead of 6 that you might expect when I animate, you'll see petal number 1, petal number 2, petal number 3, petal number 4 is on top of 1, 5 is on top of that one, and so on. So that's why when there's an odd number there and C is 0, the number of petals is equal to B. But does someone want to say what their group came up with, what they suspected the answer was when I make C into +1? Well, first of all, I'll make B 5. So when B is 5, we normally have, if C is 0, we end up with 5 petals. But does someone want to unmute themselves and say what happens with the +1, what that causes?
The loops separate.
How so? Is it? Did you mean that the loops are in between the other petals,
No, it's like one of the sets of loops becomes larger than the other one, but only one of them. So you get two sets of loops, one inside the other one.
That's exactly right. There it is. And that's what the answer is to this question. You can see it by messing around with C. So if B is odd, you end up with, and C is 0, you get 5 petals. But if C is not 0, you get petals inside of the petals. And if B is even, like we had, if B is 2 before, remember we had this guy? So that one has double the petals, but the small ones are in between the big ones, you can see. So here we go. I think this is pretty good to see how this works. So limosone with inner loop. Here it's not in between, it's in between the two big loops. Here it's it's inside them. Here it's in between them, and here's the one that we just did. Now on your, yes?
So is this just like a generalized limaçon?
Yeah,
With, like, any petals?
it's like a general, yeah. I mean, really, these are called rose curves, but it is more general. Yes, other question?
What happens if C equals B? Does anything special happen?
Well, let's see. If C equals B. So here I have C equals B. It looks pretty cool. Is there a character in SpongeBob that looks like that?
Patrick.
Star guy, yeah, Patrick.
Okay, so, but there's also A and B when those are equal, because when you get sort of the cardioids. So there's a lot of like stuff that we can do with these. Now on your graphing calculator, actually, I'll show you, because your graphing calculator can graph these, and you can see them graph in order. See here, I have 3 sine 5 theta plus 1. I did a couple of things though. I changed this thing into a little like this lollipop thing. Look what happens when I graph it. We can see the nice order of the petals. Now yours, if you have your graphing calculator, may not look quite like that, because let me show you what my settings were. So when I go to window, I made my theta step pretty small, because the default, which is like this, makes it look real ugly. Actually, not that bad. But if my default was, if my step was too much, it tries playing connect the dots. But if the dots are too far apart from each other, see, that one doesn't look that good, really. So I had to change my window to make my theta step fairly small. As far as the window went, if you go zoom standard, you get a 10 by 10, but that's distorted. So instead, after you do zoom standard, you say zoom square 5, and then at least it's not distorted, but it's kind of small. Anyway, I think that's all I wanted to show you for today. Let me stop the recording and then say a little more.